virtual commissioning of robots and AGVs with Process Simulate. We would like to welcome you to the session. For those that have questions in the lower right, there's a Q&A. There's also a chat. We prefer to use the Q&A. We do have a team of people that try to answer the questions as we go. For those questions that don't get answered now or maybe at the end of the session, we will be sure to follow up with you. Mr. Gall, can you go to the next slide? So this is the fourth, as I said. There are 3 previous ones. If you've not been a part of the 3 previous, you can request. They are online for replay. You can contact us and we can send you out that information. There's another one on subsequent to this. There's actually 2 more on March 18th and April 8th, and you can see the titles. So go next. So the agenda is just a quick introduction for myself. So I'm part of the Siemens Manufacturing Engineering Portfolio Development Team. I've been with Siemens about 20 years now in a variety of functions, and with my background being mostly digital manufacturing. Today you're going to be entertained and information provided by Mr. Gal Schneer from the product management team of Siemens relative to virtual commissioning. And then what we'll do is we'll wrap up. Given time, we'll try to answer as many questions as possible. Once again, remind you of a future seminar that's coming and the product trial that is also available to you. So with that, I will hand this over to Gal, who can introduce himself officially, and we'll get started.
Thanks, Tom. So hello, everybody. As Tom mentioned, my name is Gal Schneer, and I'm the product owner of the virtual commissioning application inside Process Simulate from Siemens Digital Industries. And today I want to talk about virtual commissioning for future manufacturing or flexible manufacturing. I know the title of the slides also mentions AGVs and robots, so we'll be talking about that today. So to go forward, I want to actually start by going a little bit back and talk a little bit about manufacturing overall. So in early days, when we talk about mass production and manufacturing in general, production lines looked kind of like this. They were manual and they were rigidly defined in the sense of not being flexible. So you could manufacture a product in high volumes with reliable quality, but you really could only manufacture one product. Any sort of change, any sort of variance in your production would be very, very hard to implement. You have to, for example, retrain a lot of people on the shop floor to get another product produced by the same line. But as technologies evolve and new systems are available, so IT systems and other types of technologies, we're able to go to a more flexible manufacturing environment in which we can handle multiple variants, configurations, more complex processes, but often the work itself stays manual, and that poses some challenges in itself. And in parallel to this, there's other types of industries or production processes where automation comes into play. So heavy automation like body and white lines, as you can see here, where the process could be significantly automated using robots, for example, but still production remains rather rigid. So I could program this line and I could even handle multiple configurations or variants within this station. But if I had to make a change, again, that change stays very expensive, very costly to make, very time consuming, sometimes even dangerous. So today's products and the competitive landscape we have for production in general, it requires something quite different from the manufacturing environment. It needs to become a lot more flexible. It needs to handle a lot more changes more quickly. And there's lots of new technologies that are emerging a lot quicker than before. There's various commercial aspects that come into play that happen very dramatically and in very short time spans. And all that means we have to be a lot quicker on our feet. So the big challenge we have in flexible or future manufacturing is to make the production a lot more flexible. So one of the key capabilities for that is this kind of a shift from automatic production to more autonomous production. So switching from how do I make the robot do what I want to how do I make the robot understand what I want to do. A good example of that are automatically guided vehicle systems, right? Autonomous guided vehicles, which are a way for us to exchange a traditional conveyor line, for example, which is pre-programmed and defined, to something more autonomous that can think on its feet, in a sense. So if future manufacturing requires us all this increased flexibility and, of course, as always, lower costs, faster speeds, and generally to make quality products and a quality process that's foolproof, and all that in a short time and in every type of industry, we need ways to cope with that. And one such way is a digital twin that essentially allows us to take the entire process of early concept design, engineering, optimization, and even following up with production and changes during construction and alongside it, and do that in a virtual environment. And with newer manufacturing, with flexible manufacturing, we also need the ability to take new technologies, things that are coming out, on a moment's notice even, and to try to integrate those into that digital twin. And that's what I want to do today. I'm going to take the example of a kitting station in a robotic facility manufacturing electronics goods. And the first step we kind of have to take in order to take our example is to create a concept for us. We have an existing facility here that assembles this box, and we want to make an automatic or autonomous kitting station for it. So we need to make a concept for this and understand how our new station will actually fit into the production. And in Siemens, we have various tools for the layout design and the concept engineering, but I'm going to put those out of our scope for today. You can find more information about those on the website or from the relevant representatives here on the call. In our case, we decided to use a kitting station with a single robot doing the kitting process and to mount additional robot arms on the AGVs, which are part of the logistics system here, in order to place parts into our station and remove parts from our station, or ready kits. Those kits will be handed over or transported using AGVs to the next station, to the assembly line. In the next couple of slides, we'll talk about exactly this, about some typical challenges we have when we come to implement stations like this that involve some newer technologies and more flexible manufacturing. So some examples you can see here, like how to set up vision systems, cameras, more classical challenges like robot positioning, which are still in existence, then how to integrate these things together using examples like flexible picking or bin picking, the programming of AGVs and how they correlate to our manufacturing environment, and in the end, we'll talk about virtual commissioning. How do we take all those things and put them together in order to test a real digital twin? So to get us started with this first challenge of the camera setup, vision systems are a very widespread technology nowadays in autonomous or in new manufacturing. They're used quite in many different cases and quite across from different industries and different kind of processes. So Process Simulate offers us an interactive graphical camera application, part of the 3D, and then also an RGB camera, which has a depth image acquisition application inside it. I want to use it for our challenge here. So our first step is to create and position a camera object in our study. And we can open a graphical viewer to see exactly what that camera can actually see and manipulate it in the graphics. So it's really easy to visualize what the vision system will be able to detect for us. Now we can try different setups of that camera. So we can try different values from a catalog, like the field of view or the resolution image of that camera. And again, be able to estimate in a digital twin, in a virtual environment, the camera's visibility and what it can actually see in our production. In this case, you can see the camera can actually see all the bins in our station. We can see all the bins laid out around the kitting robot. But if we are able to visualize it in the 3D, we can see that we have some cases where the camera can't see specific parts. So there's an angle to it, and that's easily visualized in a 3D system. So we have a couple of solutions we can try. One is to use multiple cameras, one over each bin, and one is to mount a camera on a robot arm. We're going to choose the first option of multiple cameras. We're able to get a good view of each bin. It's a more costly solution for us to test, but the visibility we get is perfect. And that means our production can stay very flexible. We can, if we have a change, if we have parts that fall slightly differently or a different bin size, we can still react to that change. And I mentioned before, flexibility here to us is key. We want to make our station as flexible as possible so we're able to cope with changes. So the challenge of the camera setup is finished. What we can do is, again, we can optimize the camera position And that's without any sort of a setup, without purchasing the equipment, of course. And we can make the assessment of what we actually need in terms of equipment. So for example, which camera would work, how many cameras do we need, how many peripheral devices, what's the height of the installation, various assessments we can make in a digital twin without laying anything in construction yet. Now our second challenge is, as I said, a more classical challenge, which is how to position a robot, how to essentially decide on a robot system. And we'll use tools inside Process Simulate like reachability analysis tools, collision detection, both a static and a dynamic version of it, and then the simulation for the robot system, which we can make realistic in order to assess the robot's motion and understand that we have the right setup, the right robot, the right position. So first we have a UR robot here, and we place it in the middle of our station, which is pretty much given, right? It's a symmetric station. Well, we want to use placement tools inside Process Simulate to make sure of that. We're able to use tools to take the targets in Process Simulate and be able to provide a two-dimensional map of the possible locations we have where the robot can actually reach everywhere it needs to, all the bins. Now, the solution we reach here is rather limited, right? There's only a limited area that the robot is actually able to reach the parts we need it to. So in this case, we decide to put the robot on a riser to test a slightly different solution in order to extend the robot's reachability. Again, we want to be able to have a lot of room to maneuver with our station. So once the robot's on a riser, we can rerun that same test, take our targets, and see that we have a much wider range of accessibility. So again, that gives us more flexibility for the future to understand that whatever challenge comes our way, the robot can handle it. This is a static analysis tool that allows us to double check that every location is reachable. And after we're done, we want to move on to a more dynamic validation. So we'll use a simulation in Process Simulate to make sure that it can reach the targets not just statically, but also when it moves in between them. So it doesn't collide with anything. There's no problems when the robot actually makes the entire motion. So as I mentioned, it's a more classical challenge that we have here, but it's still very valid in this use case. And with this, we're able to ensure the reachability, but we're also able to ensure the safety of this robot to make sure it doesn't collide, and then also double check safety concepts and avoid any serious mistake that might cost us a lot of money to change later, or if we have anything critical that happens in production, like collisions, for example. Once we have these two things in place, we have a vision system, we have a robot, we can take those and integrate them in order to use them for a bigger challenge. That would be, in our case, bin picking. So we're going to use the dynamic simulation inside Process Simulate. It's going to be slightly different than the one we saw before. So this one, it reacts to events, not just a predefined sequence of events that we want to check, but a dynamic simulation. We're able to program different brands of robots inside Process Simulate. In our case, it's a UR robot, but the same holds for different brands as well. And to connect to external application, which in this case would be an image processing application that takes the images captured inside Process Simulate from our digital twin and is able to process those in order to react to them. So the first thing we want to do is to evaluate bin picking here. And it's not a bin picking challenge, right? We have a kitting station. That means that the robot's actually going to only pick up a few parts at a time, but we want to make sure that it has good reachability no matter where that part is, even though in a real process, it's going to pick a part out of each bin. So we can use a camera application inside Process Simulate that is able to take a depth image, send that to an external system for processing, and be able to retrieve a target position from it. And then the motion simulation in Process Simulate is able to simulate the robot's pick process of that. So we can double check that the robot can reach any target dynamically and integrate it to an external application like this image processing system. Of course, we want to test, as I mentioned, every part. We want to make sure the reachability is perfect. We want to test different scenarios. So then the second target. And our goal here is to really estimate that all these are reachable and what happens if they're not. What would the robot do, for example? What will we do if the robot can't reach every part? So we'll run this a little bit faster just to double check. And we get to a point where some of the parts, you can see them already on the camera on the side there, are actually flipped and the robot can't reach those. We have 3 parts out of the 21 we started off with. So then we're able to use, again, the motion simulation process simulate alongside physical behavior to simulate how to handle these scenarios. One typical way would be to simply just shake the bin. Now we have a part that's flipped over and the robot can continue to pick and get a new target that's identified. So we're able to use the dynamic simulation and process simulate and the physical behavior model to test even scenarios that are non-deterministic, like this one. So for bin picking, we want to be able to validate the feasibility, right? It's a non-deterministic process. Parts can come in at any size or any place along the bin. We want to make sure that the robot is able to handle that. And the models inside Process Simulate, the simulation and the physical engine allows us to do this. Then we're able to estimate the pick rate, right? How many successes can we have? How long will it take us? And of course, all these inputs will allow us to optimize the rest of the production. So when we have a kitting station like ours, we're able to time the AGV that has to collect the kit, for example, based on the analysis of the bin picking we do here. So we know how long it takes the robot, what are the odds that it has to shake the bin, how often does it have to raise the bin and shake it, for example, to reach the rest of the parts. We can do some statistical analysis, and that will help us with understanding the rest of our cell and how it can cope with this flexible picking. Another critical aspect we mentioned are autonomous systems like AGVs. So in Process Simulate, we'll use the 3D graphical analysis for the motion of an AGV, like we do for robots, and the collision detection algorithm. Plus, we'll use the robotic application inside Process Simulate, because an often use case we have is a robot arm that's mounted on an AGV, like in our case. So we have the AGV motion that's coming either from Process Simulate or from an external system, right, like a fleet manager or a carpet layout. We're able to simulate that and take a look at what it looks like. And this AGV motion seems okay, but the 3-dimensional analysis in Process Simulate can help us kind of pinpoint risky areas and shed some light on them and understand if we have problems or not. So a 3D volume here can really help us understand what happens when that AGV moves under this staircase. We're able to zoom in and inspect those areas of interest really easily. And the collision detection is a discrete tool that would allow us to really see really easily if we have a problem. So whether the robot actually hits the staircase or just moves within inches of it that doesn't live up to our safety standards, we have a problem here. And we're able to use the robotic application, in this case in Process Simulate, to understand that this robot is simply not in the right driving pose. It has to be in a different driving pose, a lower one, in order to reach underneath here. So we'll test this again, shift the robot to driving pose 2, and then be able to rerun the same test to see if that solves our problem. So take this example when the robot is flushed down, rerun the same motion volume, and take a look at the results. And the graphical analysis will also kind of let us compare, right? It's really easy to see that we have one motion volume when the robot is up high, and we have another completely when we have it down low, this one here in green. And now the motion here is completely collision-free. It passes underneath and it with good clearance too. So we use the simulation tools and a robotic application for this. Of course, we'll take that input and implement it. We've made this analysis. We know this robot has to drive in a certain position, and we'll use that information later on in later stages. For example, during virtual commissioning, this will be a good input for anybody to understand that while the AGV is driving, that robot has to be in a specific pose. And once we plan for this, we can test it later when we talk about virtual commissioning. So the analysis of the AGV motion allows us to, again, avoid really critical errors like collisions here that are hard to see in sometimes on a 2-dimensional or a 1-dimensional system on a carpet, right, or a layout. And this 3D validation gives us proof that the AGV is going to reach exactly where we want and avoid any serious mistakes. The last step we have today is to talk about virtual commissioning. So we don't have such a long time. I'll take a rather specific use case for our station, but of course, virtual commissioning can encompass a lot of different values. So we're going to use some tools in Process Simulate, like the ability to connect external software, hardware in the loop, software in the loop based virtual commissioning to connect to a real or a virtual PLC, in our case, to a virtual Siemens PLCSIM Advanced. And then also the communication with a fleet manager, so an external application like SIMOVE from Siemens. And then the robotic simulation for production programs, for real programs inside Process Simulate. And we also have an internal logic evaluator that allows us to take earlier steps in virtual commissioning. So we can test the logic of the cell even without the external components in order to make it really easy to connect later to the external components and have a seamless simulation running. So we're going to test the handshake here of a manual sequence between the AGV and the PLC in our station. We are going to start a new order for this AGV. You can see the AGV camera mounted on it that shows us the view from the AGV system itself. And it goes into the station to execute the tray replacement. It has a ready kit that it's going to take out of the station and replace with an empty tray that will be filled later by the kitting robots. So the manual test here passes, the AGV comes in, the handshake is executed correctly, and it comes out the other side. Let's start another order. So again, execute it. And this time you can kind of already see, we have a problem, right? Our tray is still at the bottom position there. And when the AGV reaches the station, it's actually not able to come into the station. And that often happens. So we have to do a couple of things. The first thing we'll do is try to analyze what the problem is. So we're using the HMI in this case to analyze what happens in our station, take a manual override to see if we can fix the problem. In this case, take the turntable and raise it to an upper position. So we can check an operator solution for the problem and then acknowledge and double check the sequence again. And now it passes correctly. That's obviously not yet a solution. It's just a test we make to understand what the problem, what the root cause of it, and how can we fix it. Well, we have to fix it in a real area, which is to adjust the PLC code that controls the turntable and add here a missing branch that doesn't lift the turntable up after the first rotation. So we're able to fix the code, and using software in the loop, just download that directly to the PLCSIM Advanced simulation and rerun the same test. And this time when the sequence is finished and the empty tray is picked up by the turntable, you can see it rotates back and then lifts back up. So we can validate that the problem is solved. And of course, it's just a taste of what we can do in virtual commissioning. We will run many such sequences in manual mode and later on switch to automatic mode and test even more. And all those tests are possible by using this integrated environment that's able to have a simulation model, a digital twin, and connect to other digital twins like the PLC, like a fleet management system. And this really allows us to reduce a lot of the risks we have of collisions and mismatches and program errors that we may have on the PLC side, on the fleet manager, and of course on the robots, even before we go into construction and commissioning, and even during, so we can follow the production sometimes and test when we have mistakes in a virtual environment. So just to sum up, what I'm trying to say is that the ability here to validate these processes way before production or side by side with it at times is really a key to reduce costs and accelerate criteria like time to market, for example. And that's kind of a general value in virtual commissioning across the board, even in current manufacturing. But when we talk about the future manufacturing, flexible manufacturing, the robotic simulation, virtual commissioning becomes a really critical process. When you're integrating new technologies, this ability to virtually validate and to plan this integration of such new technology, it really enhances the ability to live up to the flexibility required in manufacturing. It becomes a crucial aspect for success of any business when you're trying to use more adaptive robotics, not the discrete ones. When you're trying to virtually commission flexible lines, flexible manufacturing at all, when you use autonomous systems like AGVs, and of course all those on top of a digital twin that's able to help you really facilitate the work across an organization in engineering and in production too. And with that, I'm going to hand it over back to Tom. Thanks you everybody for joining. I was glad to have this chance to show it to you, and I'm sure there must be some questions, so we'll be happy to answer those questions on the chat, and as Tom mentioned before. Tom?
Thank you. Why don't you go to the next one? I think that a couple of the answers are there, but stay tuned. So I think there's one in particular that you can probably address. So thank you for that presentation, Gal. That was pretty amazing stuff. For those that are interested, there is a Process Simulate virtual commissioning free trial that's available. The address is down at the bottom of this slide. This is some of the particulars that you'll see when you get to that page. It does run for 30 days, and you can, test out this whole process of connecting robots and process simulate using the Somatic software for virtual commissioning. So I would encourage those that are on the phone here to participate with that. I think it's a great opportunity to interact with the system and exercise some of the concepts that Gal spoke about today. I think most of it's going to be related to the robotic side of it, but it'll give you a good flavor for the interface. Go next. So I would also like you to mark down on your calendars, and quite a few of you will be getting invites to that because that's just how marketing people are. There is another session in March, on March 18th, same time frame, same 30 minutes. And it really refers to robot safety zones, right? This is another key aspect to programming robots, especially in not only industrial robots, but really anything that deals with robot to robot, robot to human. There's a variety of things. So I would encourage you to join that session, the design and safety aspects of programming robots and how it can impact things like shop floor. So go to the next slide. So with that, we'll do a quick Q&A. I think that there was one question on here, Gal. It says, can you speak to using the product to simulate communications between robots and PLCs? That's the first one.
Sorry, could you come again?
So the question says, can you speak to using the product to simulate communications between robots and PLCs? In other words, in the virtual commissioning space, I mean, I suspect that is, either directly through like things like PLCSIM Advanced or OPCU, but I'll let you explain.
Yeah, so there's a variety of possibilities to connect from Process Simulate to an external application like a PLC, OPC being one of them. PLCSIM Advanced with direct access from Process Simulate is another. There are a few others as well. And the information passing is based on robot inputs and output signals. And you can pretty much transfer any type of information that way. So in Process Simulate, there's controller applications that are designed for each robot vendor specifically. And we use those to process production programs, translate those into inputs and outputs exchange, and then exchange that with a PLC on the one side and the robot controller on the other side. So that's the basics of that.
Very good. Thank you. And the next question says, which imaging apps are available to connect to Process Simulate?
So today, I think we have some other information we can share later, Tom, with participants. Today we have connectivities to companies like MechMind, for example. I think we can share that information maybe later with the participants and show it. It will require a little bit more time than we have today. Okay.
Well, so that would be a part. So when you get for those on the phone, when you get a communication from us, if there's some additional information around those, simply reply, and we could actually set up a separate session with whoever wants to dig deeper into some of those questions. So with that, we're close to the bottom. There's nothing else, I don't think, in the chat window. Let's see. Maybe I'm missing it. Oh, there's another one. Which one? Oh, there it is. Profinet Communications with a question mark. There you go, Gal.
Yeah. So aside from the connections like OPC, there are also connections to tools like SIMET and Siemens, which would enable you also to use Profinet-based communication. There's actually a couple of others. And there are also ways to use the Process Simulate API to connect it to pretty much anything.
Okay. So I would say that the other questions online, we will not forget you, Ed and Krishna and Christian and Ronald. We will get to you. We can't get to you on this particular session, but we will respond to you. The questions are logged. You will get a communication from us regarding that. With that, I would like to thank everybody for their attendance. Be safe. Have a great day and an upcoming weekend. Thank you very much.